All right, last one. Here we go. So this is question number 4 from page 56. It says a motorboat accelerates uniformly from a velocity of 6.5 meters per second to the west to a velocity of 1.5 meters to the west. If its acceleration was 2.7 meters per second squared to the east, how far did it travel during the acceleration? So the big wrinkle that this question throws in is that it's got east and west included. I don't know if you caught that. So it says 6.5 meters to the west and then 1.5 meters to the west. So it's slowing down. You're with me there? So it's going 6.5 meters in one direction, and then later it's going a little slower in the same direction. It's slowing down, which means that if its velocity is one direction, its acceleration has to go the other way. So it should not be surprising to you then that it says that the velocity, or excuse me, the acceleration is opposite. So it's going to the east. It says, how far did it travel during the acceleration? So really, what are they looking for? They're looking for how far it traveled. So that would be a displacement. So that's the thing we're looking for, is delta x, which is a displacement. All right, so let's do it graphically. I think we can handle this. So now, friends, you get to pick whether you have a positive or a negative, whether west or east is positive or negative. We are going to start talking about negatives and east and west and kind of what that means. But if we use our like kind of natural compass, north, east, oops, there we go, south and west, I'm generally going to call east a positive value, and I'm going to generally call west a negative value because that's kind of what seems natural to me given our number line and our convention in that way. So I think I'm going to go ahead and call that 6.5 meters per second to the west. I'm going to call that negative 6.5, and then its final velocity is 1.5. So this is negative 6.5 meters per second, and then it's going up to negative 1.5 meters per second. Okay, and it's doing that. It's got, so we don't actually know what the time is, do we? We're just going to go to some time here where that's really the key. And so it's going something like this. So if you look at this line, you can see that the line has a positive slope, which makes sense because we have a positive acceleration to the east, right? So the slope here is positive. Okay, and the slope has a value of 2.7 meters per second squared. Okay, so it says how far did it travel during that acceleration? So we basically, if you think back, how have we done this in the past? Oh yeah, we found area under the curve, right? So that's what our goal is, and that's what our game is here, is to find the area of this thing that looks like a little trapezoid here. Now, in order to find that area, so we're going to do this little thing, but friends, remember I told you that we can kind of split this in half so we can really find the area of this triangle and then the area of that rectangle. I think we're going to have to find the time first. So let's go ahead and do that. And that should not be a hard thing. We know that slope is rise over run. And we know that the slope is 2.7 meters per second squared. The rise is going to be, well, it's going to be final minus initial, right? So we're going to go up. So we're going to say negative 1.5 meters per second minus negative 6.5 meters per second over some amount of time, but we're not sure what that is, okay? So I'm just going to rearrange this. So it's going to be time is equal to, so that's going to be 6.5 meters per second. Is how much faster we got, okay? And our slope, or excuse me, yeah, our slope was 2.7 meters per second squared. So we need to do a little division here to figure out what our time is, in fact. So let's do that. So we've got 5 divided by 2.7. So it looks like that's going to happen in 1.85 seconds. Okay, so I'm just going to double check my math here because I don't have this all written out yet. So 6.5 to 1.5 is going to be 5 meters per second of change. Yep, that looks good to me. So now we can just find our areas. So we've got 2 pieces to the area, right? We've got the rectangle that I've drawn in blue, and then the triangle that I've drawn in magenta. So let's just go ahead and do that together. So we'll do the rectangle first. So the area of that piece is going to be just the length times the width. So the change in position for that piece is going to be, well, that is 1.85 seconds times 1.5 meters per second, right? Because that's just this distance here. That's all I'm looking at is that little piece right there, okay? So I've got 1.85 times 1.5 gives me 2.775, oops, come on, meters, okay? And then I can do the other piece, the magenta triangle. That's going to be an area of 1/2 the length times the width. So that's going to be 1/2. Our length is still 1.85 seconds. The width or the height of our triangle is going to be that 5 meters per second because we've got just this piece right here, just that side. Okay, so we'll go ahead and do that. So we got 1/2 times 1.85 times 5 is 4.625 meters. And then I'm just going to add those two pieces together. So I've got this piece and I've got this piece. Bam. So I've got, oh, silly thing, come on. 2.775 plus the 4.625. And that gives me 7.4. 7.4 meters, which is what I was expecting. So good for us. Yay, team. All right. So that is our graphical approach. We're also going to do it algebraically. So let's go ahead and do that just to complete this in a full way. So we've got our givens. Again, we're always going to follow the guess method all the way out. So we've got an initial velocity. I'm going to go ahead and still call it negative 6.5 meters per second. My final velocity is negative 1.5 meters per second. Okay. The acceleration, remember, we're calling positive, 2.7 meters per second squared. And I am looking for my displacement, right? I'm looking for delta x. That's what I want to know. So I've got 4 things. I've got 3 givens and 1 unknown. The thing that I'm missing this time, if you look at the list of givens, the thing I don't know, care about, whatever, is time. So we're going to look for something without time now. And if we look for something without time, it happens to be this last equation, number 4. So that's the VF squared is equal to VI squared plus 2A delta X. So let's go ahead and use that one. So we've got VF squared is equal to VI squared plus 2A delta X. And then we need to do a little algebra here to solve for delta X. Not too challenging, though. I think we can handle it. So we've got VF squared minus VI squared. To be clear, friends, that is not VF minus VI all squared. Remember, when you FOIL out, it doesn't work out that way. So don't get tempted to do that, okay? Is equal to 2A delta X, okay? Then I'm going to divide by 2A on both sides to get my delta X all by itself. So now let's do some substitution. Here we go. I'm going to give myself a little bit more room to write. So I've got negative 1.5 meters per second squared minus negative 6.5 meters per second quantity squared divided by 2 times my acceleration. That's the 2.7 meters per second squared. Okay. And the units are all going to work out super nicely because I've got meters squared per second squared all on the top. Then I got a meter per second squared on the bottom, which means I'm just going to be left with meters. It's a beautiful thing. Let's plug it in just to make sure everything's good here. I'm going to pull my calculator out. All right, so I've got 1.5 squared gives me, I'm just going to write this out one piece at a time, 2.25, okay? And then I've got minus 6.5. Oops. Is 42.25 divided by, so I'm going to subtract those, 2.25. I could have done that in my head. That was kind of embarrassing. Sorry, don't tell anybody. That was 40. And then I'm going to divide that by 2 times 2.7 is 5.4. Divide by 5.4. Got 40 divided by 5.4. That gives me, hot diggity, 7.4. Not a huge surprise since we've been doing things pretty consistently all day. All right, there you go.